A week and a half ago, we first introduced the topic of exponents and expressions that have exponents in them, talking about monomials and polynomials. And when we were looking at the kind of arithmetic that we can do with them, the first thing that we reckoned with is how do you add monomials together? So you had this little table. What were your takeaways from working on this table? What do you remember about how to add two monomials together? Yeah.
They have to be like terms.
Okay, so the first, probably most important thing is that they have to be like terms. So, for example, we can add minus x squared and negative 3x squared. We can add those two together. Minus x squared plus minus 3x squared. How do we know that those two are like terms? They have the same exponent and the same variable, right? Their variable factor is the same. The only thing that's different about them are the coefficients. So it's okay to add those two together. And what do we get when we add those two monomials together? Negative 4x squared. So notably, when you add two like terms together, and maybe I'll put even a finer point on that, when you add two monomials together, what stays the same? Yeah, the exponent stays the same. But the coefficient changes, perhaps. Right? And just to give you some rationale for why the exponent would stay the same when you add a couple of like term monomials together, one of the analogies that I like to use is to think of the variable x as being a number. Specifically, let's think of it for the moment as being the number 10. So if I have minus x squared, for example, then maybe instead of thinking of this as a variable expression, let's think of it instead, if we set x to be 10. This is really the number negative 100. Right? And likewise with minus 3x squared. If I do the same trick and I let x equal 10, then minus 3x squared is really just a code word for negative 300. And if I'm going to add negative 100 and negative 300 together, what do I get? Negative 400, right. The negative 1 and the negative 3 add together to give me the negative 4. And the 100 just comes along for the ride, right? So it's kind of as though we're adding something which is measured in hundreds together with something that's added in hundreds, measured in hundreds. And the result is something which is measured in hundreds. We're dealing with kind of the same currency as we go along. We start with negative 1 of them, we end up adding negative 3 of them, and we end up with negative 4 of the same thing. So the reason the exponent stays the same is because we're adding two of the same type of thing together to get a third of that same type of thing. So when adding and subtracting, like terms matter, and exponents always stay the same. If I try to add together two things which are not like terms, let's say, for instance, I don't know, maybe I try adding 3x plus, where's an example? Now let's do x squared added to negative 3x. So if I want to add this monomial and that monomial together, what happens? Yeah. We can't do it. So how would you write x squared plus negative 3x? What are our options? If they're not like terms. Oops. Well, the fact that they're not like terms means we have no options. There is no other way to write this. We can't write it and make it any simpler looking. The best we can do really is just to keep it as x squared minus 3x or something like that, right? But there's nothing we can do for these two like terms when we add them together to make their sum into a single term, right? We're stuck with having them as separate terms if we try to add them together. So that was the story for addition. Like terms was the story, the name of the game when we talked about adding polynomials together. That was the first page of the worksheet. The goal now is instead of adding together these expressions, we want instead to multiply. multiply one monomial by another monomial. That's the name of the game today, is to come to grips with that arithmetic. And so we need some guiding principle that will kind of tell us what to do. So I want to take the two pairs of expressions we looked at on the previous page and look at them again with an eye towards multiplying them this time instead of adding them. So before we looked at minus x squared and minus 3x squared. I guess I looked at it this way. Minus 3x squared and minus x squared. At multiplying those two. And then we also looked at x squared and negative 3x. So let's think about both of those for a moment. Starting with the first pair. If I have negative 3x squared, and I want to multiply it by minus x squared, how would I do it? Okay, so we would add the exponents. In other words, that we're going to get an expression here whose exponent is the sum of the two previous exponents. So x to what power? Yeah. So you're saying that our end result here is going to be something which has an x to the fourth in it. So it's worth taking a moment to consider why that should be the case. Why are we adding exponents? It's actually in the reading check that you completed, the questions at the top of the stack that related to 4.2 were the questions of, can't we just add exponents? Why don't we just add exponents? When do we add exponents? And that's the right question to ask, right? Because adding exponents when the problem doesn't call for it is a very common mistake. Adding them when the problem does call for it is a good idea. So let's figure out what it is about this problem that makes adding exponents the right thing to do. And to figure that out, just to illustrate it by an example, let's go back to what x squared means in the first place. What does x squared mean, really? What does it mean to square something? Yeah, squaring something is nothing more than multiplying it by itself. So x squared is really just x times x. So that if I'm multiplying x squared by, let's say, x to the third, I'm going to change this problem just a little bit because it'll get easier to illustrate. What would x to the third mean? If x squared is to multiply x by itself, what is x to the third? What does x to the third mean? Jordan? Yeah, multiply x by itself with a total of 3 factors of x, x times x times x. So that if I want to multiply these two expressions together, x squared times x to the third, what I'm really doing is I'm really multiplying x times x by x times x times x. And so the question is, if I have these two sets of parentheses here that are kind of getting in the way of me understanding this expression better, simplifying this expression, what can I do with those parentheses to make this easier to understand? How important are those parentheses? The property is called the associative property of multiplication that says that we can just wipe out those parentheses. They don't serve any purpose when all of my repeated operations here are all multiplication. Multiply, 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 multiply. We don't need. The parentheses aren't serving any particular purpose to group those together. The answers that we get will still be the same. So I'm just going to get rid of the parentheses. And now, the question is, now that I've gotten rid of the parentheses, how many factors of x do I end up with in total? Yeah, I had 2 of them from the first factor, 3 of them from the second factor, and by the time I've multiplied those powers of x together, I've gotten 5 in total, x to the 5th. So the reason that we add exponents is because we're multiplying something which is made up of one number of powers of x by something which is made up of another number of power of x, and the powers combine. Right? That at the end of the day, the number of powers of x that we have is going to be equal to the sum of the number we got from the first factor and the number we got from the second factor, just by kind of remembering what taking something to a power even means in the first place. So another way that I like to think of this is that, as we are over here, if I'm multiplying 2 exponential expressions together that have the same base, in other words, the variable is the same, the x here is the same, then I can take that arithmetic that's happening down to the quantities themselves and elevate that arithmetic into the exponent instead. And if it was multiplication happening down here, it becomes addition happening upstairs. So if we're multiplying powers, we can elevate that into addition of their exponents. So we'll end up with x to the fourth. The other analogy we can make with this, going back to the analogy we were using before, is let's say I have 300, and I multiply it by 100 this time. Last time we added together. This time I'm multiplying. What do I get if I take 300 and I multiply it by 100? Or maybe let's make, just to make the context clear, let's make it 300 times 200. What do you get? Yeah, so we get a 6, first of all, from the 3 and the 2 coming together. But then we don't get 6 hundreds, right? Because the 100 from the 300 and the 100 from the 200 multiply together to be 100. Or another way of saying that is 10,000. Right? So those hundreds get together, then they become a 10,000. Or another way to think about it is that the pair of zeros that we got from the 2 powers of 10 and 300, and the pair of zeros that came from the 2 powers of 10 and 200, combined together to give us a total of 4 powers of 10 in the product, 60,000. So what you're seeing happen with the zeros in this digit arithmetic problem is the same thing that happens with the powers of x in our monomial multiplication problem. Right? We started with 2 zeros and 2 zeros, and when we multiplied these together, we ended up with something that had 4 zeros. Right? Same story as happens with the powers of x. Just replacing x by 10 makes the link between those two things. And finally, the only thing we didn't do in this multiplication problem is what? We didn't multiply the coefficients by one another. So -3, the coefficient of the first factor. What's the coefficient of the second factor? -1, so don't forget, when it's just a bare negative sign in the front of an expression, make it into a coefficient of -1 just to remind yourself. And -3 times -1 is going to give us, what is -3 times -1? 3. So when I multiply those two expressions together, I'll end up with 3x to the fourth. So another way to think about that is that when we've multiplied 2 powers of the same variable, 2 monomials involving the same variable together, we've multiplied their coefficients, the -3 times the -1. But what happened to the exponents? Yeah, we added exponents. There we go. So that was an example in which we multiplied a couple of x squareds together. So those were like terms to begin with, right? So we could combine them even before when we were adding their results together. But what about x squared and -3x? Those were not like terms when we tried to add them together. What happens if we try to multiply them instead? X squared times -3x. What happens? Yeah, same story. Even though they're not like terms, remember, terms matters if we're trying to add or subtract things. That's what term means, right? But the fact that they're not like terms doesn't tell us anything about how they multiply, how they come together. And they can multiply together because they have the same variable in their base, the x. So we can follow the same procedure. Multiply the coefficients, add the exponents. What's the coefficient of this x squared factor here in the front? 1. So I'm just going to wedge a little 1 in there. So our coefficients will multiply 1 times 3, sorry, -3. And the exponents are going to add. So the exponent in my first factor here is a 2. What's the exponent on this x? Yeah, so the hidden exponent, if we don't write an exponent, interpret that to mean that there is 1 power of x there. And so what exponent do we end up with once we've multiplied? What are we doing to these exponents? Again, another way to see it is that multiplication of two powers can be transformed into addition upstairs in their exponents. So the final exponent that we get here is going to be 2 plus 1, or 3. And the coefficient, 1 times negative 3, is going to give us negative 3. So even though these two were not like terms in the beginning, they are like factors to one another. We can combine their product together into a single monomial, and that single monomial that we get is negative 3x to the power 3. So then the question is, we've seen when exponents get added. What about subtracted? So it, I think, makes sense to back up for a second and identify that what we were doing when we were adding exponents is that we were multiplying powers. So this kind of tells us how to multiply two monomials. When we're multiplying monomials, their coefficients are going to multiply, but their exponents are going to add. And in this diagram that I like to refer to all the time, how I see that is what we're doing to the monomials, or what we're doing to the powers themselves. Maybe I'll say monomials, just so that the meaning is clear. We're multiplying monomials, and when we multiply monomials, according to what we just did, what we should be doing to the exponents is adding. So whatever happens to the monomials, what happens to the exponents is going to be one step lower in this arithmetic layer cake up here, this arithmetic hierarchy. Right? So if I'm multiplying two monomials together, I should be thinking about adding their exponents. So by that same logic, under what circumstances do you think that we're going to be subtracting one exponent from another? What would we have to do to the monomials in order to subtract their exponents? Yeah. We would be dividing the exponents, or sorry, dividing the monomials one by another. So if we were dividing two monomials, we would subtract their exponents. So as an example, and this example is not on this sheet, but just to get it out there. Say that I had, I don't know, 16x to the 6th divided by 8x to the power 2. How would I simplify that quotient of two monomials? Yeah, so you did two things there. You said 2 would be the new coefficient, and you also said that x to the 4th would be the appropriate power of x. So first of all, how'd you get the 2? 16 divided by 8. So you divided the coefficients. For the same reason that when you multiply two monomials, you multiply the coefficients together, right? There's no fancy arithmetic happening there. It's just a division of 16 by 8. And then where'd the 4 come from? Subtracting the exponents. And we subtract exponents when monomials divide one another. 6 minus 2 gives you the 4. So you would subtract exponents when you divide monomials. You add exponents when you multiply monomials. If we stretch that analogy one step further, is there ever a circumstance under which we would multiply exponents by one another? What do you think according to what's up here? When would we be multiplying exponents? What would we have to do to the monomials in order to multiply exponents? So addition of exponents happen when monomials multiply. Subtraction of exponents happens when monomials divide. Multiplication of exponents happens when monomials get raised to powers. So just climbing one more step on this list up here. So whatever happens to monomials happens one step lower to their exponents. If I take a power of a monomial, I will multiply their exponents. So just one example of that, and then we'll wrap this up. So say I have x to the 6th, and following Benicio's example, let's square it. What would I get? X to the 12th. And another way to see that is, again, to rewrite this, x to the 6th squared. What does it mean to square something? It means to multiply it by itself. So x to the 6th squared is the same as x to the 6th times x to the 6th. And now we're multiplying, and when we multiply two monomials together, what do you do to the exponents? Add them. So it's x to the 6th plus 6, which is x to the 12th, right? But the shorthand way for doing that doesn't involve us having to write it out every time, and will also, therefore, work if we try to raise x to the 6th to different powers, like x to the 6th to the power 5. Right? The quick way to do that is just to think of it as a multiplication, rather than converting it into an addition every time. So this little diagram can, again, kind of help you to keep things straight as far as what arithmetic happens in the exponent when arithmetic happens to a monomial.